So, this is the project I'm currently working on, and the idea is to take to incorporate models of segregation, which I developed as part of my PhD, or developed and come through collaboration with Nico Gray as part of my PhD, to see if we can start coming up with models which predict more complicated granular effects. So this is an experiment done in Manchester, but one Olivier Pulcan originally did with Jim Valance, of the breakdown of a granular front. So you start by a uniform granular material, and you let it go from, this is by dispersed granular material, and due to the segregation, there's feedback from the segregation which causes the front to break down to a sequence of fingers. Now, Olivier did the original description of this process, but what happens is the segregation takes the large material to the top, the shear in the flow transports the large material to the front, the large material is more resistive, and it causes this front to break down. So this is the problem I'm going to describe, and as I said, Olivier Pulcan and Jim Valance have already done a lot of work on this, so I'll first describe their work a bit, and then describe what difference I've done. So just to motivate it more, so the long-term goal of this project is, can we describe more complicated features of granular flows seen in geophysical things? So this is the long-term outrun of a pyroclastic density current down Mount St. Helens, and you can see at the end of the flow it develops these very poor cat-shaped profiles, and this is a long distance from here, and this is just a zoomed in view of this tip. So you've got these large, bouldery, rough pumices at the front, and you've got smoother material behind. So the idea is, can we adapt and incorporate segregation into models to sort of predict these sort of formations? But we haven't got that far yet. But just to show you a few videos to motivate it. So this is a Manchester done, but as I say, Olivier did these experiments and Jim Valance a long time ago, of the fingering. So as you can see, this uniform front starts to break down into a sequence of fingers due to segregation, and then these fingers continue. It's not a very good video, this on this projector. You can see what this large material is forming sort of levees at the front, and there's finer, more mobile thing, and these fingers split and merge and do all sorts of strange stuff. This other experiment is actually one of Jim Valance's. This is the formation of a bulbous head. This is a water-saturated flow, and at the front of the flow it forms this really big head, and I've seen a poster describing this due to one of Jim Jenkins describing this process due to modelling the water in it, but I will present an alternative way of producing these bulbous heads due to segregation, which is not something we're after, but a consequence of the model we developed is that we can form these bulbous heads due to segregation going on. But fundamentally it's the same sort of process, because there's a mobility difference between the segregated and non-segregated material. So it's exactly the same sort of thing at the front. And then the long-term goal is to look at these even more complicated flows. So this last flow is the USGS flume experiments, where there's 26 tons of material falling down an 82.5 metre chute. These are water saturated, but by dispersed, and you notice so this material is flowing down this chute, and you notice that it comes to the bottom, this material does not spread out due to the segregation. So we've just switched to the overhead camera view, and this flow carries on, and does not laterally spread out much at all, and you can see there's these levee walls forming, and now we'll switch to a camera view at the side, where you can see what these levee walls are fairly rich in large materials. So this is just looking at the flow out again, and it's not too, so I think you can convince yourself what there's large material forming these levee walls. So even in these water-saturated flows, there's some processes of segregation feeding back and changing the flow properties. So that's the sort of problem. So for this talk, just to introduce the coordinate system I generally use, we're talking about flows going down an incline, and as I said, there's bi-dispersed flows, and the segregation going down on. So x will be my downslope coordinate, and z will be my normal to surface coordinate, and I consider some sort of mixture, and as it flows, it segregates out to take the large material towards the front, and the small material, on average, is sort of going towards the back. So that's sort of the conceptual picture of the things that I'll be talking about. Whoops-a-daisy. So I'm just going to go through what's been done before. So we'll be using a Savage-Hutter shallow waters type theory. So these equations have been presented a few times before now, but often this friction coefficient here, which is the friction, is taken to be a Coulomb friction. Here we'll be using the friction described by Olivier Pulcan, a much more complicated friction law, and we'll be looking at that. So that's the modification. So rather than being standard Savage-Hutter, we'll be using for the friction coefficient a Pulcan style friction law. So just to say, and I think this also has been presented a few times. Well, yeah. So this is just the friction law, which was experimentally, which was experimentally determined, described by Olivier Poulican for granular materials. So it's got two angles, which are the minimum flow angle and the maximum flow angle. It just gives the correct. Well, it was experimentally derived, and it is very powerful, and it can predict all sorts of things on flows, including the correct front shape for flows and things. So yeah, it's just it's a first step towards introducing the proper rheology to granular materials. So we'll be using that. So Olivier, in his first paper, also did a stability analysis of these flows. So he came up with the idea these things. It's the segregation which causes these things to break down. So he said, we'll introduce C to be a depth average concentration of the small particles. They didn't have a model of the segregation. So they said, well, we'll say the friction some sort of linear combination of a large particle friction law and a small particle friction law, and take some linear combination. And because they didn't have a model of the segregation, they just took this, they took a sort of, they assumed the small particle distribution followed some sort of tanh function. And then their analysis led to the conclusion monodispersed fronts were stable, but biodispersed fronts were unstable as long as the large material for a given depth and velocity was rougher. So they concluded these fronts were stable, but if the large material was rougher, i.e. when it's segregated to the front, you got more resistance, these fronts broke down. So what we're going to do is, because we have a model of segregation, is to take this segregation model and run with, remove this assumption and see if we get the same conclusions. So that's where we're going to go. So next, this is the model of segregation we developed as part of my PhD, but won't say. So phi here is the concentration of small particles. U, V, and W are the downslope, cross slope, and normal slope velocities respectively. And so this was originally applied to, so in my PhD work we took U, V, and W as prescribed functions and derived some simple solutions. So this is just considering the flow out of a simple hopper. So we're assuming there's no cross slope, and the vertical velocity is something like that, and we get these solutions. So here, we're plotting the volume fraction of small particles. So we're flowing out of a hopper where there's mixed material, and as this material flows out, a long time downstream, it's segregated into the large material being small, and you've got these. So the solution consists of three shocks, two shocks here and one shock there. And what's actually going on in these problems, if you consider a small particle coming in here, the small particle percolates down past the large material, leaving it up. So the process is, the small material percolates down, leaving the large material up. So the small particles coming down, leaving the large material up, and eventually it's percolated down and pushed all the large material, pushed all the large material out the way. So enters a region of pure small particles where it's perfectly happy and carries on. And similarly, you can figure this line here as there's a small particle just there and it starts to percolate down straight away. Starts to never use a Mac. It percolates down straight away, so you instantaneously form a layer of pure large particles at the top. And this is just a similar solution for a more complicated situation, sort of mathematically, but an easier situation to do experimentally, where you place the small particles initially on top of the large particle. And the reason we're interested in this is because it's a slightly mixing grains, as everyone probably knows, is very hard, and to control the degree of mixing is hard. So this is a much easier experiment to do, so a much better situation. So here you place the small particles on top of the large, and you get this much more complicated structure. But basically, this line here represents the first small particle percolating downwards. So this is the first small particle percolating downwards through the layer of large material below it, pushing the large material up, and eventually this small particle reaches the base where it's perfectly happy and travels along. And then here you've got small particles traveling along which are perfectly happy, but as they come across large material which has been driven up by the small particles before, they start to travel down and they cross this shock there. So if you're interested in the it's not going to give me long, is it? If you're interested in the mathematical structure of that, it actually consists of two curved shocks, one straight shock here, which is segregation, we call it the segregation shock, and in this region here, there's an expansion point contained. So that's where we started with the segregation stuff. We derived these simple shoot flow experiments, and there has been, again, these are just some experimental pictures, again from Manchester, but Vaughan and Savage and Lund did some very good experiments on this, where you can take, but you can see what, again, in these simple shoot flow experiments, you get the same sort of thing. You do eventually get distinct segregation of the large material on top of the small, and you've got a region of mix, and you can see these layers thickening. These are not the world's greatest experimental pictures, but you can see the point. So we're going to take this segregation model and couple it with a Savage-Hutter style shallow water, and then take this assumption of this linear volume fraction scaling for the friction laws, and take two Poulin style friction laws, and see if we get the same results. So so the first thing we have to do, because we've got a depth averaged shallow water equation and we've got a three-dimensional segregation equation, we have to do something there. So what do? To add in our segregation dynamics, we depth integrate the segregation equation. So we introduce, like Olivier did, depth average concentration C, but this is the depth average concentration of our segregation equation. And we take a limit. So we have this SR parameter, which is the segregation rate. And to do this, we take SR going to infinity. So this is assumption what materials segregate very quickly. This assumption, yeah. So, yeah, but in reality, so we take the assumption that materials segregate very quickly. And I'll come back to that assumption a bit later, but it's required for the depth integration because you have to assume something about the vertical structure. So we take the SR limit, so we assume everything's already segregated in that sense. So this depth integration process leads to this, which is the depth integrated three-dimensional segregation equation, where now C is the depth integrated concentration. So we're going to proceed. I'm going to plug my laptop in next time, as Olivier did, and take shallow water Savage-Hutter style equations with mu, where so these are just already seen several times, the sort of Savage-Hutter equations, and where mu here is going to be a linear combination of two friction laws, where C is this depth integrated concentration, but this is the difference. Our C is taken from this equation, where U and V are the velocities from the depth, from the shallow water style thing. So now we have this fully coupled system, which does segregation and shallow flow. So, and yeah, this is just the friction law. So we've got two friction laws. So we're going to do the same trick. Do we get the same results? So the first problem I'm going to consider is, there's lots of numbers here, but basically I've got two materials, one rougher than the other, and the rough one's going to be my large material. So the key angles are all given here. I actually borrowed these from actual measured materials, and we're going to run it on a shoot of 28 degrees. So we have large material which is rougher than the small material, because these numbers are bigger than that, and this is running on a shoot of 28 degrees. And I'll go through this movie a few times, but we'll run a movie of what happens. So there's lots of plots here. Notice the aspect ratio to fit it in. So these are very long compared to shoots. So this is plotting the height, this is the downslope velocity, and this is the depth integrated concentration. So I'll start with this one. So in the depth integrated concentration, you can see what we are getting large material travel towards the front. This here is large material, and we have this growing layer of large material at the front. So, you know, the segregation, the equivalent of the depth integrated segregation material is taking the large material to the front, which we know should happen, but it all remains nicely two-dimensional. But something else is happening. If you look at the height profile, you notice we're getting some sort of bulge in the height profile here. So I'll just look at the center line numerics, and from that we can say a little bit more. So this is just plotting it at the center line, where this is the velocity, this is the concentration. Again, you can see this pure rich region large material. But what we're forming here is these flows form this sort of bulbous head shape as well. But this is nothing to do with, as Jim Jenkins' poster does, nothing to do with water segregation. This is just to do with, this is just a perfectly dry model, but with biodispersed material. But as the large material segregates the front, because it feels higher friction, it holds up the front, and this bulbous head forms, which grows to a limit, and then goes to a limit in the sense what the height of it tends to a constant, but its thickness grows with time, and this head just grows in that direction with time, and it propagates nice and steadily down slope. So we didn't get any breakdown. But we do understand this. No, okay. So we do understand this solution a bit. By considering the balances of forces or work done against it, we can work out the speed of this region here, the speed of the front. So this formula actually works for giving us the speed of the front. And then this shape here is just exactly the Poulkan finger shape, but with the large material, because this is purely large. So at the front of this flow, we've got a perfectly large material-rich Poulkan finger, and we know the front velocity, and we know this velocity because it's set by the inflow condition, but we're not quite sure what's going on here, where there's this little small, relatively small rich region at the back of the head, which is always there in the numerics, and we don't know why. So this is the inflow concentration, where it's strangely 45% small and 55% large, but the relative small concentration just increases at the back of this head, but then drops to very rapidly. I almost believe this is a shock, but I don't know for certain. Drops rapidly to a purely large head, which is exactly the Poulkan finger shape propagating at the front of that. So as I say, we understand this a bit, and then from that, because we know it's the Poulkan finger shape, we can predict the height of this head because we know it's the Poulkan finger shape. So that formula gives us a recurrent head. But there's an interesting thing when you write this in here. If you lower the angle such that the larger material is going to stop, you don't get a result for the height of this back of the head. You can't get a result for the back of the head. So that leads us to what we're going to do next. We're going to do exactly the same simulation with the same material, but at a lower angle. So now we're going to pick the angle where the mixture will flow, but the large material will not. So this is exactly the same material again, but a slightly lower angle. And what we get, it's not so distinct on the height profile. It is if you leave it long enough, but straight away in the concentration profile, you remember this blue stuff is the large material, this red stuff is pretty much small, rich material, and it's segregated out into fingers, with the small material being filtered down the center of the finger. So again, if you watch this move slowly, you can see the order it goes is the segregation starts to build up and you get the large front building up. It causes a reduction in the velocity at the front, and then that causes perturbations to appear in the height, which propagate through this flow. So, is that the end of the story? Well, no. We suddenly realised there was a problem, or numerically there's a problem. So, it all looks fine and dandy, but this solution is not resolved numerically. So, the more grid points we throw at this, the more fingers we get. So we can't do a waveform. So we are missing something in the model. I'll just briefly say that. So, yeah. So we can form fingers at angles where the large materials stop, but the number of fingers we get is grid dependent, so we are missing something. So now the head solution on the other side, just before we get fingers, is perfectly well resolved. You plot it with 400 points and 600 points, and you cannot tell the difference. But as soon as we go to the point, and this solution is well resolved up until the point it fingers, but when it fingers, we do not get a determined wavelength. We are missing some piece of physics or done something wrong. So we are missing the piece of physics which does the wavelength selection of the fingers. But we got the ballpark. I think we've captured the ballpark physics which monitors process. But we have thrown away something in the depth integration. Maybe it's the segregation length. Maybe it's you can do more complicated segregation models with diffusion in. So these are both concept. Is the assumption of instantaneous segregation chucking away a length scale? Is the fact we're neglecting the more complicated segregation models with diffusion throwing away the length scale? So we have thrown something away. So we are missing a length scale. We have thrown something away, but we need something. And I think I've done about right from the timing for 20 minutes. So the conclusions are we have developed a couple segregation and bulk flow model, and the coupling is done by a linear combination of two Poulkan-style friction laws. The model predicts fronts are stable if a pure phase of large material flow. The numericals are well resolved for the propagating head solution and all appear fine, and we get the front is only unstable if the large materials stop. But after that, our numerics are completely grid dependent and we don't know what's going on. So we are still missing something, some piece of physics which will determine the wavelength of these fingers after the instability. Thank you.
I think I have a guess of what you are missing. In the Saratoga model, you ignore these shear stresses.
Yeah.
And I think there, where you have the fingers, these shear stresses become important.
Yeah. So good possibility.
One of the things that we've noticed when you're actually forming complete heaps at an angle of repose and you get this sort of segregation effect, one thing you commonly see is what's often referred to as a Christmas tree
Yes.
effect. Does this mechanism explain that?
Yes, because the Christmas tree effect you can explain with just periodic avalanche and segregation and then deposition. So you've got an avalanche, it segregates, it deposits, you've got 2 layers, avalanche, deposits, 2 layers. So that Christmas tree effect can be explained with this model with periodic avalanching and deposition as it comes to stop. That makes sense? Yeah.
There's 2 effects there. One is the periodic avalanche, and that in itself can cause and contribute to it.
Yes.
I'm thinking the instability of the head, that's
Right.
then stopping, and then the other material coming over it.
Yeah, okay, possibly. Yeah.
Nicolas done that in his habilitation thesis.
Yes, yeah. There's a paper on that, so yeah.
Done any sort of analytical stability analysis for the rivulet for formation that you see?
I would love to, except there's a problem. The base state is not steady, and it's not only not steady, it's rapidly evolving. So, and I don't know what it is. So, it's not steady. It's not a similarity solution. I'd love to do the stability analysis of this problem, but unfortunately, I don't have a base state to start from. So, yeah.
Are there any more questions? Well, if not, let's thank